This isn't your neighborhood. Neither is this, or any of these. And it isn't even this. Looked at from a wider perspective, your neighborhood is a big cloud of gas. Astronomers say the solar system is moving through the local interstellar cloud, also called the local fluff, because of its low density and irregular shape.
The gases are mainly hydrogen and some helium. There are trace amounts of heavier atoms like carbon and oxygen and nitrogen that are just floating around the interstellar medium. We know that the heavier atoms in the interstellar medium are left over from previous explosions of stars as supernovae.
The local fluff is 30 light-years long, about 180 trillion miles. It's inside a larger, chimney-shaped gas cloud called the local bubble, also the remnant of an ancient supernova. The bubble is 300 light-years long and lies in the inner edge of one of the spiral arms of the Milky Way. And that's our neighborhood. At least, we think it is.
Our exact position in the Milky Way galaxy relative to the arms actually isn't known. The structure of the galaxy is not known in any real detail. Some people think there are 2 major arms, some people think there are 4 major arms. It's hard for us to determine the exact structure of our Milky Way, where all the arms are and so on, because it's kind of like a mouse being inside a maze. You don't get the big picture.
In almost any Earth neighborhood, you can determine your location very precisely.
Turn left in 30 feet.
But when you're dealing with something as big as the Milky Way, GPS isn't an option.
The galaxy is, 100,000 light years across.
Even exploring our local neighborhood involves a lot of uncertainty. But if we did have a galactic positioning system, it would probably locate us about midway between the top and bottom of the Milky Way, and about midway between the galaxy's outer edge and inner core.
Our solar system is about 26,000 light-years away from the center of our galaxy.
According to one hypothesis, we have a very exclusive location.
There's one idea that only stars in a certain range of distances from the center of our galaxy are in the so-called galactic habitable zone, that is, able to have life on planets surrounding those stars.
It is just the right place with a star of the right temperature and a planet at the right distance for there to be a lot of liquid water on the surface where the chemistry of life began and evolved into us.
The overall range of the galactic habitable zone extends from about 13,000 to 35,000 light years from the center of the Milky Way. The main part where we are ranges from 20,000 to 29,000 light years from the core. Inside the zone, old neighborhoods have been destroyed to make a place we can call home.
Depending upon how you look at things, our local neighborhood, our local solar system is actually a relatively safe place compared to what seems to be going on if you look at the universe in the large. In the early history of our solar system, it was a much more violent place, and the material that formed the sun and the planets was still sorting itself out. There were all sorts of collisions and violent things happening that gave rise to this nice, calm, or relatively calm place that we have today.
We think that the earliest stars formed out of hydrogen and helium alone, but that over time, the stars work as these processors that create the heavier elements. This is important because when those stars eventually die and explode, These supernovae, or stellar death explosions, seed the galaxy and the material around it with heavier elements.
So, for example, the carbon in our cells, the oxygen that we breathe, the calcium in our bones, the iron in our red blood cells, all those are heavy elements.
We know that the sun is at least a second or third generation star because there are planets around it. There are things made of iron and carbon and other heavier elements.
But the processes that led to life on Earth don't seem to exist outside the zone. Closer to the edge of the galaxy, fewer massive stars have exploded, producing fewer heavy elements.
Further out in the galaxy, you don't have as many atoms like carbon, nitrogen, oxygen, the atoms that are so important for the chemistry of life. So the habitable zone of the galaxy cuts off at a distance where you just won't have the heavier atoms to make life.
If the outer galaxy is a bad neighborhood, the inner area is even worse. Gravity from massive gas giant planets could tear us apart. And there are other dangers the closer you get to the galactic core.
Back in the times of Copernicus, we thought that we were the center of our universe. And even as we started to learn more about the heavens, eventually we still thought that we were the center of the galaxy. Now that we know even more, though, it actually turns out that we're lucky we're not in the center of the galaxy.
At the center of the Milky Way, sucking matter and even light into it, is Sagittarius A star, a black hole nearly 14 million miles across, with a mass 3.7 million times that of our Sun.
Yeah, the galactic center has a black hole in it. It gives off a lot of radiation, enough to fry life as we know it. So you can't be too close to that. Then there are other regions in the galaxy that are also probably not so great for life because there's just so much radiation from nearby really hot O-type stars.
O-type stars are giants. They're hotter than the Sun, 10 to 50 times as massive, and throw out titanic amounts of ultraviolet radiation. With these stars, you don't worry about sunburn, but extinction.
It's probably not easy to survive in an environment where you're in a tight cluster with a lot of O-type stars.
O-type giants can destroy planets before they form.
The radiation from these stars is so strong that it actually sweeps the material away from these newly forming would-be planetary systems and rips it out of the orbit of their stars.
If you want proof, look at the Rosette Nebula. It's 5,200 light years away, far outside the local bubble. But it shows what O-type giants could do to our neighborhood. A 2008 study by the University of Arizona of 1,000 stars in the nebula found star after star had been made barren by being too close to a blue giant. So what's a safe distance from the radiation of an O-type giant?
Well, if you ask me, you can never be too far away from a giant. If you're life like us here on Earth, we're used to our fairly tame sun. You want to be probably at least tens of light years away, maybe more than that. Really, just don't get too close.
Like a city between a desert and an ocean, our corner of the galaxy thrives between two different, inhospitable regions. With the elements of life and without the threat of intense radiation, it seems like our neighborhood is literally the only place to live. But is our place in the Milky Way really so exclusive?
The idea of the galactic habitable zone is that if you're too close to the center of the galaxy, there's all these crazy things going on and it tends to kill off life. To be honest, I'm personally skeptical of the idea because I think that life can happen in all sorts of environments, or at the very least, we don't know. So we should be open-minded. It's possible that our kind of life can only live in this galactic habitable zone, but elsewhere there could be other kinds of life that we would call extremophiles. On the other hand, they would call us extremophiles.
One thing is certain. In our neighborhood, we have a sun that, unlike a blue giant, protects us from danger and destruction in ways that we're still learning about. That protection may be invisible. But if we lose the sun's protection, our neighborhood could be doomed. Our place in the Milky Way seems pretty peaceful because, like a lot of communities, we don't give much thought to the 24/7 security systems that keep the bad stuff away. Many cities on the edges of rivers or oceans have dams and levees to protect them from floods. If the dams and levees fail, disaster. We've got threats and defenses on a galactic scale, too.
Space is filled with radiation, known as cosmic rays. Cosmic rays are bad for us in the same sense that nuclear radiation here on Earth would be bad for us. Because high-energy radiation tends to disassociate carbon bonds, which is what we're made of. What you're really doing is damaging your DNA, and there's a potential there that you could start to have mutations based off of that.
Some mutations can help a species survive or lead to extinction.
There's no evidence that cosmic radiation has really negatively impacted Earth in the past, but it's nothing that you want to play around with.
Our neighborhood's prime defense against cosmic rays? Magnetism.
We have this zone of protection in our neighborhood. Of course, the Earth has a magnetic field due to how things move around in the core of the Earth. The Sun also has a powerful magnetic field, and it also has the solar wind. These phenomena actually generate ways of protecting us from things that come from outside the solar system.
The Sun's magnetic field is twisted by the solar wind. Streams of charged protons and electrons that shoot out of the Sun at 1,000,000 miles an hour.
Then the particles that live in the solar system between the planets actually stretch the lines of the magnetic field around in complicated patterns.
The solar wind carries the magnetic field more than 3 times farther out than the orbit of Neptune. But 9 billion miles away, at a place called the heliopause, the solar wind runs out of steam and slows to almost nothing. As it slows, it twists the Sun's magnetic field into a barrier against cosmic rays from interstellar space. This is the heliosheath.
If it wasn't for the heliosheath, these cosmic rays would actually pour into our solar system all the time. The heliosheath acts as a kind of shark cage for these incoming cosmic rays that might otherwise influence our planet.
Some do come through, but they don't come through as strongly as they would without that protection.
It used to be thought that the heliosheath was a rather elegant barrier made of flowing curtains of magnetic force. But recently, enter Voyager 1 and Voyager 2, probes sent out from Earth in 1977. In the early 21st century, these disco-era devices sent back information indicating that the Sun's magnetic field lines don't flow smoothly together. They break up and reform into violent magnetic froth, and each bubble in that froth is 100 million miles wide.
We used to think that it was a smooth, nice barrier between them, but in fact it's a roiling place with all sorts of bubbles and patterns. I think there's always been people who think the universe is more elegant than it is, and people who think it's more violent than it is, and we're always surprised one way or the other. The truth is that some aspects of the universe are quite elegant, and in other aspects it's quite a mess.
Where are the elegant areas of our galactic neighborhood, and where are the rough parts? It can be hard to tell with all that gas and dust in the cosmos.
It's sort of like looking here. Behind me is Hollywood. There's even a landmark there, the Capitol Records building. You can barely make it out. And even beyond that, there are some hills that are even hazier. It's because there's stuff in the air that blocks the view. The hill itself obscures my ability to look beyond it, and that's kind of like the dust in very dense molecular clouds. When you hit a big wall of a dense molecular cloud filled with dust, you can't see anything.
When we explore our galactic neighborhood, what we see depends on how we look at things.
One of the things we've learned through the history of looking at the sky is that every time you look in a different way, you see new things. And looking at the sky a different way often simply means looking in a different part of the electromagnetic spectrum. As we look up into the sky with our eyes or with the aid of optical telescopes, in the visible part of the spectrum, we see the night sky, and there's a lot to see, but it's only a fraction of what's out there.
Some space telescopes see through cosmic dust with infrared vision, similar to that used by commercial infrared cameras.
I've brought with me this plastic bag, and when I put my hand inside of the bag, you can't see how many fingers I'm holding up. With the infrared camera, you can see the heat coming off my body. So my face, which is warm, is red and white, but my hair, which is cool, shows up as blue. So with the infrared camera, you should be able to make out how many fingers I'm holding up, even though you can't see through this bag. That's how astronomers peer through cosmic dust when they want to see things that are hidden from sight. For example, stars being born are very warm, but they're obscured by dust shells. With infrared, we can see them.
Certain objects are transparent or opaque depending upon the frequency of the light that's trying to get through them. And so, in fact, something that's getting in the way, like a lot of interstellar dust or gas, is getting in the way of what your telescopes can see, are actually invisible in another part of the spectrum. You can see what's behind.
With infrared and a multitude of other wavelengths at our command, we've discovered a lot of neighbors we didn't know we had.
There's a whole array of instrumentation which is exploiting that lesson that if you look in a particular part of the spectrum, you see the sky in a very particular way.
From what we've observed, it looks like some old neighbors might have helped life form on Earth, while some newer neighbors may be planning to wipe us out. As we've explored our place in the Milky Way, we've met a lot of interesting new neighbors. But there are good neighbors and bad ones.
Good neighbors are, for example, objects that are in predictable orbits, moving around, doing their own thing, minding their own business. We can look over and wave to them, but they're not going to do something sudden or dangerous to us. The bad neighbors then would be things that may do something unstable. They may do something that could affect us in a way that we can't predict when it's going to happen. So that might be when a star dies and explodes. Or it might be when something collides and bounces off something else and comes spinning in our direction. So classifying things roughly into good neighbors and bad neighbors is really a classification into predictability and unpredictability, or violence and non-violence, if you like.
Sometimes a good neighbor will bring a moving in gift. That might have happened to us billions of years ago, as the Earth was still cooling and forming out of recycled material from a recycled sun. We might have received a gift that changed